All right, so picking up where we left off last time, I went back, if you guys maybe noticed while I was scrolling through here, and put in some of the slides, the screen stuff we did on the board. Working off of the condensed presentation here. So I know there were a few times in streams when I'm like, where the heck is that slide? I'm sure that'll happen now that we're talking about groundwater as well. So, bear with me as I appear unfamiliar with my own work. I don't always use this, like I said, this condensed presentation. So, all right, anywho. So this is all connected into the hydrologic cycle, the water cycle. We talked about once the water falls back down to the earth, there's a couple options for it. All right, it stays at the ground as what we call runoff. Stays at the surface, what we call runoff, and that was the streams that we talked about. And as I indicated, streams has its own chapter. Groundwater has its own chapter. The other option is that it percolates or infiltrates. They use a couple different words. Trickles into the ground and stays there for a while, what we call groundwater. It fills up these reservoirs that we're going to call aquifers. People use them for wells, even townships. Cities and stuff can use groundwater. It's not just somebody with a well. There's a whole nother sub-tangent on here that we really don't get into. It might get mentioned once or twice, but about pollution. It's really easy to picture polluting a stream, okay? But somehow it's a little harder to understand, imagine what's going on when you could pollute groundwater as well, okay? But like I said, we really, unfortunately, don't get into that, even in the full presentation. So groundwater is water that's in the ground, as opposed to surface water being water that was on the surface. This is another one of those slides with a whole lot of embedded vocab, a whole lot of concepts. We'll be on this slide for a while. All right. So you're going to be seeing a lot of these cross sections. And this is us looking into the earth. All right. Picture you're driving along the road and there's a big cliff, a rock cut, okay, an outcrop as we call it. This is a very similar idea. And the first thing I want to draw your attention to is the blue and white halves of the ground. And more so the little enlargements off to the side. So the big difference in those two is the color white on the ones on top, right? Well, that is there to show that it isn't all blue. The blue is water, obviously. Okay, and what we're dividing this into is vocabulary words all the way over here, understandably. The saturated zone, and we don't have a word for it up here, but the unsaturated zone. We keep it nice and simple, all right? We could just put the word un in front of it. Let's do that for a change. What is saturated? Well, pore space. All right, awful lot of talking about pore space. So think about all the sand you've seen in your life. Maybe the hunk of sandstone isn't the best idea. Maybe think of a conglomerate or a breccia that you saw in lab class, perhaps. These aren't perfect little cubes. They're also hardly ever perfect little spheres, okay? They are these random shapes. And because they're these random shapes, when we do bunch them together, think back to talking about lithification and making these rocks. Even then, when we compress them, compact them, throw some glue in there, there's still empty space. That glue, coincidentally, goes into pore space as well. Okay? But even after all that, there's oftentimes plenty left. That's where the water goes. It's hard to imagine a hunk of water flowing through the piece of sandstone or the conglomerate that we talked about a couple minutes ago. but there is space in there. So the saturated zone is telling us that all of the pore space is full of water. The unsaturated zone, not quite. Okay. We say air, we say gases. We're supposed to say gases because when we think of air, we think of, you know, straight up the nitrogen and oxygen that we breathe, and the composition can obviously vary a good bit. That lid was not even on. All right, and we're back. For you folks at home, I just spilled my coffee, so I had to pause briefly. I think I was talking about air and gas. I'm not sure. So we're supposed to say gases, but we use air interchangeably. All right. So what separates the saturated and the unsaturated zone then is the water table. All right, you see that little black line there. And the water table, I think the best way to talk about it is that it marks the top of the saturated zone, okay? Some people like to say it's the bottom of the unsaturated, but it is literally a plane, a surface, a table. That's why they could use this word. This obviously represents three-dimensional, right? So that line goes into the cliff, and it is effectively a surface. Obviously, there's rock above it and so on and so forth, but it's a tangible thing. You guys tell me, is the water table fixed? Does it move? Can it move?
Yes.
Okay. What kinds of things can make it move?
Floods, heavy rains, streams.
Well, so let's just talk about a couple of those. Floods and heavy rains. What would that do to the water table?
Make it rise, wouldn't it?
Make it rise. Good. Somebody else. What might make the water table fall? What might make it drop?
Drought.
A drought. Good. Anything else?
I want to say fire.
I
Like
suppose.
a wildfire. Something that dries the ground out real hard.
Interesting. I suppose that could certainly happen. That doesn't come up in our Family Feud list of top, however many there, but that's certainly a possibility. Usually we think of usage, though, is the other one I was fishing around for there. When we first came to town, Nirvana Water, I think, had more or less just opened up, early 2000s. And there was a bunch of hubbub in the news that everyone, all the surrounding areas, their well levels had dropped a good bit. Nirvana bought land that was previously a sheep farm, is my understanding. I used to love Nirvana Water. It had that really, had a good flavor, and I used to say, sheep. But, so it's been used as a sheep farm, and certainly that had a usage level. Got to water your sheep so they grow and all that stuff like that. But you put in a water bottle distribution factory, that's going to be a lot heavier use. And that's another thing we need to think about, is that when we talk about these aquifers, it's really easy to picture a little pool on the slide in front of us. But these things can be not just neighborhood-wide, but, several miles. So, anywho, so the water table can move. The water table separates the saturated from the unsaturated zone. We either see water in the pore space or water and gases in the pore space, just to summarize all of that. Okay. I'm not going to worry too much about capillary fringe. Let me just hit two more things here. Capillary fringe is a lot like these paper towels ideally would have done, which was absorb. Okay? Capillary fringe is that little bit above the water table where some of the water trickles up. Picture a good Bounty paper towel, right? That's capillary action. But not a vocabulary word you need to worry about. Also, vadose zone we don't discuss. I've just never got around to browning that out in this situation here. Yes, sir. Question?
Which pore are you saying for pore space? Are you saying holes, or are you saying dumping things?
O-R-E.
Okay, so holes.
Yeah, holes. Porous. Think porous. I had to think about it. I'm like, O-U-R, oh, yeah. Oh, not O-U-R. And I know some people who would mispronounce poor to be poor as well. So I didn't know where you were going with that question. All right. And you see the rain up there just to remind us, of course, how we fill up. One of the ways we fill up this groundwater, okay, is through trickling down. It's probably the only thing they haven't labeled on here is that trickling. We got a well. We're going to talk all about wells in a little bit, though. So there's just the vocabulary again, just to make sure we got it. All right. Again, there's a lot of information on this slide. I think this came from me attempting to again, make something condensed. But we still talk about it for the same amount of time. So let's just worry about the first word right now. Aquifer. I use that word once or twice. Okay. An aquifer is that body of rock or sediment. They always say that, or sediment. That yields a significant amount of water. Generally, when we talk about aquifers, we're going to talk about sedimentary rocks. Okay? Yes, there's a handful of instances where some of the harder rocks, you might hear people talk about a granite aquifer, especially in New Hampshire, Vermont. Okay? That can happen. They don't have pore space so much as giant cracks. And there's its own inherent benefit or two and detractors with that. But those are an exception. I want you to think about sedimentary rocks when we talk about aquifers. Because to be an aquifer, it's implied that you have both a good porosity and a good permeability. What are those? Well, they're the next two vocabulary words we're going to talk about. So going back to our conversation about pores a couple minutes ago, porosity is a measure of that pore space. Okay? You want to think of the aquifer as 100%, that whole body of rock as 100%. And then of that, what percent of it is actually pebbles and sands and silts and clays and whatnot and cement? And what part of it is pore space? What part of it is holes? We joke sometimes that porosity is holosity, okay? But somebody might put a W in front of there and get confused. So it literally is a measure of the percent of pore space in a body of rock or sediment. I like to think of a sponge that's probably sitting on your kitchen counter right now, okay, by the sink. Or any sponge. If you don't have one there, that's fine. Just picture a sponge. All right, you can picture SpongeBob. All right, you could measure the volume of SpongeBob. And you take his length times his width times his depth, right? You could do the same thing with your kitchen sink sponge, and you'd get a number. Well, how much of SpongeBob is actually spongy material? And how much is those holes?
I mean, he does look absorbent.
He's very absorbent. He is. And that's actually another totally different value that we're not going to talk about. But so going back to the average kitchen sponge, let's just throw a number out there and say that it is 70% sponginess and 30% holes. Okay? You would say that kitchen sponge has a porosity of 30%. It's pretty straightforward. Okay, if it was somehow 50-50 or 80-20, I've never actually measured the porosity of a kitchen sponge. Maybe I should one of these days. But spongy material versus holes. And again, back in reality, it's rocks and pieces and bits and not versus the holes in between them, the pore space in between them. All right, so that's one thing. And that arguably measures how much water it could hold, right? Because that's where the water goes. But we have permeability. And again, not a word you're unfamiliar with. You've heard of permeable before. In this case, though, permeability measures the interconnectedness of those pores we just talked about. And believe it or not, you could have one without the other. You could have plenty of pore spaces, but they're really sort of random and scattered. not really connected. I picture the stereotypical hunk of Swiss cheese right now. Okay, it's got those great big old holes in them. But unlike your kitchen sponge where if you pour water through it and it kind of absorbs and eventually trickles through, you pour water on top of that big hunk of Swiss cheese, it's just going to go everywhere because those holes aren't connected, right? So that would have a low permeability. I made up a word a long time ago, flow through ability. That's what permeability measures. How easily can the water flow through it? So an aquifer ideally should have both a good porosity. We want a lot of water to be able to be in there. Otherwise, we're not going to waste our time tapping into it. And we want to be able to get that water out of there. Now, in the normal semester, okay, I do have them here. In the normal semester, we talk about some variants. And those are down at the bottom here, aquitard and aquiclude. All right? And arguably, these aren't aquifers because, well, they don't fit the definition of having both a good porosity and a good permeability. But I think if you were a hydrologist out there doing work, this were a hydrology class, et cetera, these words would come up because you'd be measuring the effectiveness of some of these stones. Okay? So an aquitard, as in retard, to retard means to slow down. All right? And so the water has, what will you guys tell me? Is that a low porosity or a low permeability? The water moves slowly. We're saying there's water there. It just doesn't flow very well. So which one is that? Yeah, so an aquitard usually would be something with low permeability. You'd tap that if you had to. Be a pain in the butt to get the water through, but it is there. Aquiclude, as in exclude. All right. Now, strangely, there is water in there, usually. We'll talk about why in a moment. But it ain't going anywhere if there is water. I like to think of aquiclude kind of like Tupperware. It's an impermeable membrane, okay? Whether it's low porosity or low permeability is beside the point. This is a natural impermeable barrier. Shale is a great example. Silts and clays are what we call hydrophilic. You've heard of hydrophobic, afraid of. Phobic means afraid of, right? Philic means loving. So silts and clays are hydrophilic. They attract water to them, basically. So much so that they don't like to get rid of it at all. So shale carries on that tradition of absorbing all kinds of water, but then it just holds on to it. It's coming up on the season, unfortunately. We had our first snowflakes this morning. You'll be driving down the thruway, Route 90 here fairly soon, maybe. And you're going to see those beautiful ice flows coming out of the outcrops there. In the spring and the summer, those are usually little waterfalls. You can't really notice them. It's not enough to see it, but it builds up quickly as ice. So you get those really cool ice flows, which are coincidentally kind of bluish looking. They're so white. Each of those is more than likely at a layer of shale. Okay? What happens is the water trickles down, and that stuff is so fractured to begin with. But it hits a fairly solid layer. The water builds up, and it flows. That way it happens to be, around here, it happens to be tilted towards the thruway, so the water flows that way. Okay? But you'll see this out there in nature if you're wandering around through the woods. There's other reasons for waterfalls, little trickles of water, but oftentimes that's a real good one. When we talk about building an aquifer, okay, we'll talk about some idealistic aquifers. We're always going to have shale on the bottom because it gives us a bottom to our aquifer. Gives us a bottom layer. You may or may not know when they talk about building, when they build landfills. One of the things they like to put down is a layer of clay nicely compacted underneath it. Okay, just again, sort of as a trap. I think they also put liners on them, but liners can be poked and punctured and whatnot. But that clay, it's a good shield. Okay, so the big vocabulary word here is perched water table, but there's also, as I said, a handful of things in all of these slides to talk about. We'll do the first one first, though, perched water table. That's that little water table up in the upper left there. And another word for a perched water table sometimes is a false water table. What happens, we have a lens of shale there, okay, that is catching the water. And, you know, it's really hard to get scale here in these images. But arguably, you know, maybe a small household could make do on the water that's caught by there. Somebody mentioned, I think it was Peter earlier, about streams affecting the water table. Okay, there's certainly some connection there. We'll probably talk about that in a little bit if the slide's still here. But they can feed a water table. In this case, though, you're probably just getting water from rain and snow melt. Okay, and that is quite likely to dry up. Now, well logs are public record. Any town you go to, that you can get the well logs, what your neighbors drilled to, so on and so forth. If you're like Mr. G and you hire the cheapest person to do the job all the time, you may not get someone who does that. And again, it's hard to tell scale, but he could drill in and say, okay, well, I've been having water here for 100 feet. You should be good. That's always the Klitschner right there. You should be good. I say, okay, here's your $10. Thank you. $2,000 job. I got it done for $10. That's what I get. Well, come midsummer, okay, we're sucking air through the pipes because we're nowhere near the water table. You know, if we had looked, everyone else was 500 more feet down, for example. All right, so I know you guys aren't exactly in that position right now in your lives, more than likely. Friends or family might be. Okay, but if you ever hear people talking about drilling a new well, or you get some property up north, okay, always check the local well logs to see, you know, where everybody else's well is. Because we want to be into the main water table, not one of those false ones. All right, another thing that shows up on here is the word spring. Now, I know we just got off a chapter where we told you that geologists call everything that flows a stream, regardless of if it's a creek, da-da-da-da-da-da-da. We got one exception, and that is spring. And you may have noticed that I did not mention spring in that long list of words that we call rivers. A spring is when the groundwater intersects with the topography, with the lay of the land, with the surface. So a spring, a true spring, so spring water, you got bottles of it at the store, so on and so forth. True spring water is supposed to be leaking out at the surface. It's groundwater leaking out. A natural spring. And in this case, they have another perched water table, that shale of lens, catching the water. Technically, I suppose we were just talking about them with the throughway, making those ice flows in the winter. Arguably, those would all be springs. You guys have lived here a while. You're probably aware there's a handful of places where people like to pull off the road and fill up their bottles. You do that if you want to, especially when people have gone so far as to pound a big old PVC pipe into that. And I worry about the algae content. I really do. But lots of people have done it for, you know, family generations. There's one up 12 a little bit. There's one down 8. Okay, and enjoy. Somebody brought me a bottle one semester, and I did that really fake but polite, you know, pretending to drink thing. Held up my lip. That's good. You know. But germaphobe. I was a germaphobe even before COVID. So, but lots of great spring water. Okay, Read those bottles of water you're buying, by the way. I can't remember the exact name of the company now, but one of them, it was either, one of the big ones, it was Aquafina or...
Polar Spring?
Polar Spring... Poland Spring is legit. Polar is, that's the carbonated stuff. Nestle, maybe. Anyhow, it's like bottled in St. Louis. It's St. Louis Municipal Water Supply. Or somewhere, okay? Check the bottles. Now, mind you, you're getting, 24 of those water bottles for, $1.98 or whatever. Okay, fine. Yeah, what do you got there? Is that that looks like Poland Springs. That's good. That should be. Where does it say bottled at? I think they're like legit. Somewhere on there it'll say. Yeah, and you do have to worry about that if it's a creek out back too. It's not necessarily held to the highest standards, but well, you look, you let us know when you find it. Saratoga, by the way, those pretty blue bottles of the glass ones in it. That's not even bottled in New York State anymore. I just saw that the other day. They're selling it at the throughways and everything. Did you find it?
It's probably sourced in Maine.
Okay. They didn't write the word probably, right? You're saying probably?
No, it's
Okay. But again, it could be, Maine Municipal Water Supply, city in Maine. But, Poland Springs is supposed to be really good stuff. That is true. But some of these others, just, it is what it is. Clean. It's good, clean water. But nothing fancy. All right, so springs, groundwater leaking out at the surface. All right, finally we're going to talk about wells. And in that we're going to talk about a couple types of aquifers that I haven't mentioned yet. Let me see what slides I have to do this conversation with. I do not have another. Well, I have the vocabulary words. All right, let's go to the vocabulary words first. So we've got two kinds of aquifers that we're going to talk about, a confined aquifer and an unconfined aquifer. I'm going to show you pictures of both. So I just want to get the vocabulary words out there. Anecdotally at the moment, a confined aquifer is pressurized, and therefore any well we tap into it would be self-flowing. An unconfined aquifer is unpressurized, and therefore any well you tap into that is going to need a pump of some sort or another. Be it the old-fashioned hand pump like at the parks. I don't even know if they still have those around. I haven't seen any in a while. Or a motor. Okay, any of you who have well water more than likely have a pump motor somewhere. You know that if you don't have a generator for a power outage, you're not going to have a whole lot of water for a while. So on and so forth. So let's get those terms out of the way. Again, unconfined and confined aquifers. All right. We're going to talk about an unconfined aquifer first. No, you know what? I see why I do confined first. We're going to talk about confined first. It's confined in that it has a capstone. It has, what do you guys remember the dashed rock symbol was? Limestone's bricks. Shale. Shale. And the dots? Sandstone, good. And the little pluses, we're going to just pretend that's, random rock. We don't care what that is. All right? Because once we hit that shale, that's the end of the aquifer. Well, this one also has a lid on it. It's got that shale on top, too. And believe it or not, that makes this kind of work like a pipe. A tube. Even though, again, this is 3D, and yeah, it's going into the board, and there's not a shale bending around and touching to the bottom. I don't mean that kind of tube. But having a top and a bottom on it, it confines it, okay? And the water flows through that sandstone in the middle. Now, there's a couple issues with this. First of all, any water that falls where that shale is just going to flow downhill, right? Once it soaks up in the shale, everything's just going to roll downhill, not go into the aquifer. The only place you could recharge, that's how you fill an aquifer, by the way, recharge or refill is up there where the sandstone is cropping out. If you were walking around up there, you'd see some shale, then you'd see some sandstone, then you'd see some shale. Well, that little bit of sandstone right there is the only place that the rain or the snow melt can get in. That's very limiting, obviously. If you think back or just take this layer of shale off the top, you can fill the whole damn thing up anywhere it rains, right? But in this case, only right there. So these are kind of tough to refill or recharge. Now, they made this super simple because they put it on a slope, all right? If you put anything on a slope, you're going to have some inherent energy. But not only do we have the capstones, we have a slope going on here. So they have made this, again, a very nice teachable sort of thing. You've got pressure. Now, you've all seen water towers, right?
Yep. So
it's easy to think that they put water up there to keep people from messing with it, right? You don't want someone, teenagers hanging around partying and doing this or doing that, or some sinister person putting some poison in it, so let's put all the water way up high. Well, that's not the reason they do that. Why do they put the water way up high?
increase potential energy.
All right, potential energy for the rest of the folks out here, what would we call that with regards to water?
Pressure.
Water pressure, all right? It's to make water pressure. We're doing the same thing here. Now, in hydrology, you've used that word a couple times now. They call it head. I don't know why they call it head, but they call it head. All right? So we have head 1 and we have head 2 in this case. Head 1 is at the top where the pressure gradient starts. Head 2 is at the bottom where the pressure gradient is ending. And unfortunately, you get to have all these wonderful conversations about good head and bad head, and it gets kind of, yeah. All right, but they just do it obliviously, like they don't know anything else. But anyhow, so I won't put you guys through that. But there's a neat little trick you can do. See this well here, down at the bottom? This is artesian well. This is the title of the slide. An artesian well is a self-flowing well. Okay? Picture those old-timey movies where usually when they're out there going for oil, and they poke a hole in the ground, oil shoots up, everyone's dancing around it, going, woohoo, yeah. Same thing here, but with water. So an artesian well is a self-flowing well. It's self-flowing because it's coming from a confined aquifer, which are under pressure. Now, this red line, this is where I was just saying there's a neat little trick you can do. Not that I endorse this, but I'm just saying. All right? The red line is there to show you that that head is going to try and equal itself out, at least momentarily. So that water should shoot up to the top of the aquifer. Head 2 should shoot up to head 1, if ever so briefly. So, you can win a little money, maybe, on weekends with a neat little trick. If you happen to have with you 3 things. You need a funnel, you need a length of tubing, and you need a liquid. I'll leave the liquid up to you guys. The water works great, though. All right? So, what you want to do is you want to attach this length of tubing to the end of the funnel. And you want to hold the funnel in one hand, kind of like your Statue of Liberty. All right? And then on the other part of the end of the tube, you want to put your thumb over it. Okay? You want to seal it up. So you need a partner here. You're going to have someone fill this up very slowly, and you take your thumb off the bottom, let the air in, let it all fill up. All right? All right. Now, what happens if you take your thumb off? Standing here doing this, arm up in the air like Statue of Liberty, your thumb's down here, it's all full of liquid. You take your thumb off, what happens?
Water comes out.
Exactly, the water comes out, all right? And you could do that once for effect, just in case someone wasn't aware what would happen. Here's where you make $5. You say, okay, I bet I could take my thumb off and no water will come out. How do you make that $5?
Keep the thumb on the end that's in the air.
Okay, don't let any. Well, no, I can take my thumb off and no water will come out.
Step on the tubing.
Step on the tubing. Yeah, without kinking the tubing. Hold them equal. Remove the head. Exactly. All right. You could lower one hand. You could put the one hand all the way up there, I suppose. But it'd be easier to lower the hand that's up there. Bring them equal. All right. Bring the top of the funnel or the top of the liquid equal to where your other hand is. Take your thumb off. You should not get any flow because you've removed the pressure, removed head from the equation. All right. So left unchecked, that obviously would drain out the aquifer. So oftentimes you'll see, we'll go and we'll put a plug of some sort of piping system on there so that doesn't flow out. Those aren't everywhere. Those aren't super common. Where you have them, obviously, it can be quite nice. We're going to go back to this slide now to talk about the other type, the unconfined aquifer. We're going to presume there's a layer of shale down there somewhere, okay? Has a bottom because it's filling up. There is, however, nothing consistent on top to cap this off. It can recharge anywhere it wants to, short of these pesky little lenses of shale. But otherwise, any rain, snowmelt, etc. can trickle right in and fill up your water supply. Again, these are really nice for that purpose. However, when we poke a hole down into it, like we see the well in the middle here, what happens? Absolutely nothing. Okay? There's no pressure. There's no head. So you have to either load, one of the earlier slides had the old bucket well, okay? They boarded all those up decades ago because evil children kept crawling out of them. But no, you don't really see those so much anymore. But obviously, people have well water. We've got pump systems and so on and so forth. So you've got to suck that water out like a straw, okay, in some way, shape, or form. That's good for a couple reasons. It's bad for a couple reasons. I think they're both fairly obvious. Your water isn't going to go anywhere. That's sort of a good reason. But also then you have to spend energy to get that water out. So again, an unconfined aquifer does not have a capstone. A confined has a capstone. I think that's the purpose of this slide here. Okay, it doesn't mention the capstones, but confined is pressurized because of the capstone. Unconfined is unpressurized because no capstone. Confined aquifer then is self-flowing or artesian. I think it's named after a region in France, Artesia, where they first kind of, I don't want to say discovered these, but they made it popular or something. Okay. Google it later. And then a pump well is the other kind of well then. If it's not a self-flowing artesian well, it is a pump well. And believe it or not, this is sort of 3 or 4 questions right here on the test. Okay, we talked about how interconnected all this confining layer and so on and so forth is. There's a lot of questions. Streams has a decent amount, but this groundwater is slightly higher level cognitive stuff here. So put some extra time in when you're reviewing this stuff. So we do have one negative issue that we're going to talk about with pump wells. There's a couple. Again, obviously you have to suck the water out in some way, shape, or form. But you have to be careful how quickly you suck because you can use up all the water surrounding your well. Remember, this is rock, right? I don't know about you guys, but when I was at a park getting water out of one of those old pump well things, and again, I know maybe they don't have those everywhere, but you kind of know what I'm talking about. I don't know what I thought was down there. I never thought about it. Maybe a giant pool of water at the bottom that we were just somehow pulling the water out of, or some such thing. But I sure as heck didn't think that I was sucking it through rock, okay? Because that just seems silly, doesn't it? But that is what's going on here. Yes, you've got a hollowed out area. You have a tube through it in this case. So it's really not hollow anymore. You've got that confining layer there. You're giving yourself a tube. But down underneath it, that water's got to flow through rock. It takes a little bit of time. Now, they usually talk about refresh rate, something similar, for those water to percolate back into those holes. Obviously, that's related to permeability, one of those first words we talked about. So if you have a highly porous and highly permeable rock that your well's tapped into, for that little cone to go away, should be a lot quicker. But again, it varies with use. This is actually something you're familiar with, whether you know it or not. I call this the slush puppy effect. Okay, picture back a few months ago when it was super hot and you stopped somewhere at the Quickie Mart, got yourself a slushie or whatever, and you're sucking, and not enough to get brain freeze, obviously, but you're really hot. It's good, and then you're like, what the heck? Nothing coming through. And you look down, and what's really happening is you're sucking the liquid out of the ice, and it sort of leaves that glacier valley around on the inside. You've cleared out, look next time, you've cleared out around the straw first. Okay? Exactly what's happening here. So what you got to do, you got to shake your cup a little bit, let everything fall back into place, and you're good to go. But you can't really shake this. Okay? But it's the same idea. It clears out around the pipe first. We had well water. One place we lived, oh God, it was years ago now. It was a house, big old farmhouse, divided into 3 apartments, and then there were actually 2 trailers, 2 elderly families in the back, and then there was a barn. It was a big barn. This was out in Ohio. It was probably a corn farm. And we were all on one well. And I was new at this. I was adjuncting at a local community college there. And, I knew a little bit about this, but I didn't have the worldly experience yet. I'm like, really? Everyone's on the one? Oh, yeah, it's good. Except for around the holidays. You think about it, around the holidays, you're cleaning more, you're cooking more, maybe you're doing more laundry, you're running more water, you got company, toilets are flushing more, sinks running more. Every so often around the holidays, we would get a little air through it. And again, maybe if you have well water, someone that does. Every so often you'll turn on the spigot and you go, and then it'll flow. A little bit of air got in there.
What do you mean, the sprinklers people have in your gardens? Or
impact sprinklers?
No, you're not going to want to. No, you're not going to want to definitely use sprinklers. You wouldn't want to use sprinklers with well water. I don't think that would be a good idea. I'm sure
yeah, that's right. Yeah.
some places might, but yeah, no, just there's air gets in the pipes. That's all I was saying because of a situation like this. The pipe sucks in. It hasn't refilled quick enough. Somebody else goes and turns on the water. Remember, I was in this scenario. We had 5 different families pulling off of that same pipe. So somebody might have just used a whole bunch to do something. Someone else then did, and it makes that cone bigger and bigger and bigger the more people use it, even though it's trying to refill itself, to recharge itself. So that's called a cone of depression, at any rate. Cone of depression. And it's about drawdown around the pipe on a pump well. It is an issue.
I think that's also what they call the thing they put on your dog after it has surgery.
That's cone of shame.
Close enough.
That is right. Call of shame. I get done tattoos.
All right, so this at this point, because of how I talked this morning, this at this point sort of serves more of a summary, okay? GW stands for groundwater. And if it seems like I'm really belaboring the point with a few of these terms, it's for a good reason. Okay, you're going to see them. All right. Two more vocabulary words. Gaining streams and losing streams. Gaining streams and losing streams. What are they gaining and losing? Well, obviously water. But where is the question? What fills a stream? Where does a stream get its water usually? We mentioned some earlier.
Runoff.
Runoff.
In this case, the water table.
Well, where, generally speaking, let's look at B. Yeah, let's look at B, not A. Generally speaking, where does a stream, where does runoff, you mentioned, where does runoff come from? That's what I'm looking for here.
The top.
Yeah, but what is the runoff? Don't say water. Rain. Okay, so precipitation and what's the other one we always say? What melts?
Ice melt.
Precipitation and snow melt, or ice melt. All right, precipitation and snow melt. Those are your two sources of surface water, 9 times out of 10, okay? Yes, all those other things you guys said are true, but we got to get the water there first. All right, so that stream is arguably fed by precipitation and snow melt. Varies with the season, okay? Now, the stream on the left is also fed by the water table. It's in contact with the water table, at least in this diagram. So it gets fed by a third source. So when you don't have snow melt, when you go into an extended period of time without precipitation, it still has a little source of recharge and refill. Okay? So it's gaining, it's called a gaining stream because it's gaining water from the water table. The stream on the right, however, is above the water table. And because gravity, etc., the water is going to, even though it's busy flowing downhill, mind you, but it is going to trickle through, percolate down, and fill up the water table. Don't worry about that little hump there. Yeah, that's probably true, but we don't need to worry about that. It's going to fill up the water table below it. Which stream do you think is most likely to run dry first?
The one on the right.
Yeah, the losing stream. Exactly. Okay, because not only is it subjected to lack of snow melt and a dry season, okay, what water's in there is trickling down to the water table, and so you're losing water 3 ways in that case. Now, some of you overthinkers out there, and in this case, bless your hearts, because it's a good thing, you're like, okay, well, wait a minute. Over back here to A, you said there's no snow melt and it stopped raining, and the groundwater is at the level of the stream, so it's feeding that, but isn't that going to affect the groundwater? Yes, it is. Okay. We told you a while back that the two sources of water for the groundwater are also precipitation and snow melt. So, yes, it's a losing game long term for the gaining stream here, but in this snapshot moment that we're talking about, it's winning. And he was right also, by the way, we talk about, we've had all these conversations without talking about, uphill. This water, we established that back with the hydrologic cycle, the very first lecture in this conversation. But you got to think about what's going on uphill all the time with regard to groundwater, with regard to surface water, all right? Especially as we're developing the lands like crazy. That's one of the big things they were tossing around with Sequoia Creek, is all the development outside, all the development. What they really mean is pavement, okay? And or taking the trees out. But the more you pave, the less water is going into the ground. The more water is staying at the surface. So they've been good last couple decades or so, ideally, building these catch basins. Think around Sangertown Mall there, okay? That's what Sangertown Mall was, a marsh, a swamp. All right, so was Yanadahasas, apparently. The golf course there, the country club. They drained that, probably, and made the Sangertown area worse. And then they built up and left these huge catch basins. They're a lot bigger than you would think. You see the one as you're going into Targets there. You see the one off to your right. But the expanse off to the left towards Olive Garden and all that stuff is big. And I didn't really even know that. As a student, just like you guys one semester, who, I hope he worked security there or what he did. But every so often they'd have to go out into those trails there, I guess. And it's a big hunk of land back there. Big hunk of land. And it's all marshy, swampy stuff. So if you leave places like that, the water can stay. Okay, but if it just flows downhill, going back to the point, okay, the more concrete we put, the more blacktop, whatever words you want to use, and all those areas around you are now not percolating into the ground and draining downhill. It's changed over to all downhill. And we do see that problem a lot. Because again, there's a reason we can talk about streams and groundwater in the same essential conversation. We took a break in between, obviously, but they're connected, okay? And if that wasn't the whole point of the hydrologic cycle, you know, at least part of one of the whole points, you know, then you missed something. So just want to make sure now that we're there, you're putting it all together. And hey, how about that? Who knew I had a slide about that? So they do interact all the time, okay? You may have heard of an intermittent stream. You may not have. I don't think we've got one on our topo maps for around here. Instead of the solid blue line that they usually use on a map for a stream, if you see a dash of the blue line, that is an intermittent stream. Intermittent is in it doesn't run all the time. Losing streams tend to go dry. We talked about springs being the interaction of surface and groundwater, like the epitome of it. Puddles. How do puddles make it in here? Well, you guys tell me. Let's try and use some sciencey words here that we talked about. Why do puddles form?
Because of mud, dirt, water, rain.
Well, what about the mud, dirt, and water?
The water that is in the puddle.
It's not as porous. There's an option. What did you say?
Yeah, I was going to say basically the same thing as him. The water that is in the puddle cannot find a way to percolate into the ground.
All right. And so we're looking for the reason why. And he's saying maybe it's not as porous. What is another reason? There is another reason. And it happens to be the right one. There you go. Because at the moment, at any rate, you're saturated. Whether it's arguably the water table or not, but at least for that moment, that clay, sand, and silt is all saturated. Maybe that's what you were thinking, why it can't go anywhere. But that takes time to trickle down. We've been talking about that. So puddles form, at least in grass. Obviously, cement, we know why puddles form, okay? But we're talking about in your backyard, for example, in a field. And that's because the rain came too fast, or the snow too much, and it just hasn't trickled away, so you get that standing water. Well, that's essentially what a lake is, all right, or a pond. This is a big puddle. Those, ideally, are connected to the water table. All right. In fact, that's how you get those usually, not from precipitation, but marshes and swamps for sure. Right? A marsh or a swamp, think about it, it's way more vegetated. It's not exactly a shallow lake or a shallow pond, but it's where the water table is obviously at the surface, but that vegetation was there first. And over time, stuff that wasn't tolerant to that much water. Again, you guys aren't necessarily in the place where you're taking care of houseplants and whatnot yet. Some of you might be. But when you get to your point in life and you're taking care of watering tomatoes, maybe you help your folks do your garden or whatever, some things you could overwater very, very easily. Some things you just need to, set water next to them and they're good for another month. That sort of stuff naturally takes care of itself. and you get vegetation, cattails. Everyone knows what a cattail is, okay? They're incredibly tolerant of standing in a puddle of water for Lord knows how long, all right? They don't die out, but I don't know, I'm just going to make something up. The rose bush, I don't actually know how tolerant roses are, but I can't think of another plant right now. The rose bush dies out because that's way too much water for the rose bush, all right? And that's this evolution of environment down here. This is the last thing here. And I think we might have mentioned this once or twice. Evolution gets some people all jacked up in a bad way. That's usually not even biological, animal. All right. Very few people have problems with evolution when you talk about it from the angle of vegetation and from environments. They're like, well, yeah, the cactus isn't going to grow there. That's too much water. They like no water. That's why they're in the deserts. Okay, well, why do you think they're in the desert? So nature sorts that stuff out. The problem comes in when we try to meddle in the business. It worked out at Sangertown because it was already a swamp or a marsh. Right when I told you I was teaching at a community college in Ohio, right when we were doing that, they decided to build a new Jeep plant. And for whatever reason, they had to have this particular plot of land that was a wetland. And they had a wonderful bit of legislature that says if you want to destroy a wetland, you just need to build a wetland. And having just had even this 3-minute conversation about an evolution of environments, can you just put a wetland somewhere?
No.
No, not unless you're going to constantly feed it water and so on and so forth. Right, but on paper, for the Congress people, it made sense. So, yeah. It wouldn't be there if it wasn't supposed to be there, so to speak. So, but these things change. And as the water levels, be they anthropomorphic people or not, all right, we might decide to build a city next to an old swamp, and we drain a lot of that water. Or for agriculture, we drain a lot of that water. We actually use it, and we ship all the plants away to, all the produce away to another part of the country. You're taking that water out of this part of the water cycle, you're sending it to another part of the water cycle. That is going to turn into a field eventually. It'll no longer be a marsh. So on and so forth. So, at any rate, it is all connected. It is all interwoven, intermingled. And yes, we certainly can have an effect. I like to keep hope up in the back of my mind that Mother Nature is bigger than all of us combined. But we certainly can have some drastic temporary effects. Okay. So a couple drawings here that show how springs can happen. And as I said, it usually involves groundwater leaking out at the surface in some way, shape, or form. So you noticed this bottom left one here. What were the bricks? Limestone. Water and limestone, no good. If you have hard water, that means there's calcite in your water. That water flowed through limestone somewhere on its way to your house. All right. Karst, yeah. So water dissolves limestone rather easily. Water will dissolve everything eventually, okay? But limestone, very quickly. So the rocks, the earth, it's old, it's cracked, obviously. And we told you that water flows through pore spaces. Well, water obviously will flow through any cracks that are there as well. So the top image here is showing you some cracks that have enlarged because water sat in them and dissolved the limestone out. And that's usually not a problem because as long as there's still water in there, well, it's solid, right? It's even though it's solid with water in some places, it is still solid. But should the water level lower itself, and we've obviously had a good bit of time between A and B here, because in A you still see all these little, they look like little gopher tunnels or something. But down by the time we hit to B, those have grown a good bit. And additionally, we've lowered the water table. So now you have these big open cavities, which we call caves. Not every cave is formed this way. A lot of them are. If you've been to Howe's Caverns, this is what's going on there. And they talk about during the Ice Age and so on and so forth. So water, dissolving limestone, and all of the associated features you get from that is what karst is. Okay, this one is a German word, I believe, and it comes from an area in over there. We've got tons of limestone here too. Could have just as likely been called Utica or something, But so they call it karst or karst topography. I think our next slide is going to show you a bit more of a landscape. This isn't all pretty stuff, though, unfortunately. There is some pretty stuff. All right, stalactites and stalagmites. What did you guys learn back in Earth Science or wherever to remember which one is which? Which stalactite, which stalagmite? Or did you never learn the difference? Hold on, he's got one back there. Go ahead. Oh, you lost it. But what was the little thing that you used to remember that? Or wasn't there one? Hang on tight. Okay. All right. I don't know which one of you was first. Go ahead. What did you learn? Or you didn't learn anything, you just knew?
I'm trying to remember my Bill Nye days.
Okay. I don't know what he said on that one. What did you got? Just remember it. Okay. So my teacher said, think mites, bugs. I'm like, okay, we've got bugs on the ceiling and on the ground. That never worked for me. It took me, sadly, till my teaching days, probably far bit into my teaching days. Stalagmite, G ground. Stalactite, C ceiling. So stalactites, well, you got to hang tight. That's a good one. All right, so you don't fall off the ceiling. But just remember, because again, 2 points on the next test here. Which one is the ceiling down? Which one is the ground up? These are dripstone formations. So you tend to see both. All right, what happens is the water, after dripping for years and years and years, it leaves a little bit of residue behind. Basically, the calcite that it dissolved out thousands of years before that. Water level goes down. All that water's still around there, okay? And it drips. So you get a little residue on the ceiling, and then you get a little residue underneath it on the ground. And that builds up. And believe it or not, they have something called columns. I think it's in one of the pictures, where a stalactite and a stalagmite will join, and they just call that a column, thank goodness. But, I didn't hear you. But, all right, so stalactite, stalagmite. Unfortunately, there's a dark side to karst, and that is our sinkholes.
Florida.
That's Florida.
No, I didn't say that. You did.
No, I don't think it's Florida, but
Florida is several coral reefs just sutured together. So Florida has a lot of limestone, but so is just about everywhere. Remember, the oceans at this point have been practically everywhere on this planet. Even at the top of Mount Everest, as we saw in the video the other day. But that doesn't mean the oceans were that high. All right? It's that rock was down low. Yeah. So at any rate, it's a little hard to get scale on here. If you look to the far right, there's a road. I'm not going to call it a highway exactly, because even after all these years, I still haven't exactly counted the lanes. But it's at least a 3-lane.
it looks to me like a 4-lane personally.
So,
But this is in Florida.
I don't know where it is. I don't know where it is. It's not a picture I took. It's a picture I stole years ago, and even the textbook apparently didn't seem that I stole it from didn't seem necessary to cite it. But at least in place here. But So let's just for argument's sake call it a. I agree it could be 4 lanes, but we're gonna say 3 lanes. Maybe there's some shoulder there, just to give you some concept, because part of that sinkhole did take a bit of the road. All right. So now we see, okay, we've got some scale there. Holy cow, this is big. You look up to the top, you see what maybe was a factory or possibly part of a mall or something, and then down below we see more of that. And this sucker just collapsed. Maybe there was some sagging, some stuff leading up to this, but quite often these things just happen. There's always stories of some poor soul who was asleep in their bed, kind of like the Pompeii stories, but just asleep in their bed and just fell into the earth. What's really hard to gauge here is depth. Okay, they don't need to be too horribly deep for it to be catastrophic, obviously. But again, to go back in the conversation, everything is fine until the groundwater leaves, because then there's no longer anything to support it. And it could just be, time. It could be something silly, a big old semi-truck pulling up with a delivery, and it's just the last straw. And it caves in. And again, anywhere where you have limestone and a fairly, wet environment, these are a concern. Not just Florida definitely comes to mind, but even here, back in Ohio, especially places where we did a lot of coal mining at, because you've got all these tunnels everywhere that let water flow through even more easily. Now, speaking of states and cities, one place you do hear about this sometimes is on the news, and you'll hear a sinkhole opened up in downtown Utica today. A UPS van fell into the river, or not fell into the river, fell into the road. Those aren't sinkholes. All right. Similarly, if you know Waterville, there's I think it's Schoolhouse Apartments or something like that it's called. And a good while ago, 10 years ago probably, giant sinkhole, use the word incorrectly again here for a moment, opened up just right in front of this place. It's still there. I have no idea why they haven't fixed it. There's a fence around it. It's grown in. It's interesting. So what's happening there, 9 times out of 10, is actually weathering and erosion. What runs underneath all the city streets, or at least adjacent to them?
Sewer pipes.
Sewer pipes and water pipes, and sometimes steam pipes. All right. And those things have been there for 100 years. They're old, they leak. And you wouldn't think that a little dribble here, a little dribble there would actually move sediment, but over decades, it does. So whether it's the fresh water, whether it's the sewer water, it doesn't matter. You're hollowing out underneath your road little by little, day after day, forever. And then one day some poor sap drives up, gets out of his truck, goes in to get a sandwich, comes back out, and the truck's in the road. It does happen with some frequency. End of the news, again, we'll say a sinkhole opened up. No. Okay, the road collapsed, yes. Something very similar happened again. I think you guys were probably tots at the time, but they tore up Genesee Street for a long time, going all the way to downtown and fixing all the pipes down under there, because somebody did just that. And they realized that it was a problem, and I don't know if they got a grant or what they did, but they found the money to fix. It was a big project. So yeah, it's not just all cool going into caves and looking at stalactites and stalagmites and whatnot. There's definitely a bad side to it. Yeah.
For the record, my estimate is about 36 to 50 feet deep.
Based on?
Based on my imagined size standing on that sidewalk.
Okay. I'm not seeing the sidewalk. The road, kind of by the road there?
Yeah.
Where's the sidewalk?
To the left, the telephone pole standing on it.
Okay. Interesting. Yeah, it could very likely be. It's hard to tell. And even that 50 feet down, 36 feet down, that could be enough to obviously destroy some fun stuff.
It's a lot, yeah.
So another neat little sort of folklorish thing. with this is you go back to the old pirate days, be it the rum runners up on the Great Lakes or down on the coast. The coast is easier to explain because of the tides, and this brings in Goonies, of course. You guys have seen Goonies. A pirate ship getting stuck inside is slightly exaggerated there. But there were definitely places where you could only access during low tide. Okay, you go in. During high tide, the cave is flooded, or at least the entrance to the cave is flooded. But at low tide, you could go in with a small boat, put all your booty up in there and everything like that. And again, they did very similar. You don't have tide so much on the Great Lakes, but they certainly have a lot of these limestone caves there too, and they would hide the rum in there. But yeah.
You mean pirates as in like Pirates of the Caribbean, or pirates as in like Somali pirates?
Not nowadays.
Oh,
The old timey pirates. I imagine the Somali pirates might do similar.
I mean, they hijacked the Maersk, Alabama.
What's that?
The Maersk, Alabama. The Somali pirates. There's a whole movie.
There's Somali pirates in Alabama?
No, Maersk, Alabama, the cargo ship.
Cargo ships. Okay.
Yeah.
Okay.
Yeah, you ever heard that story?
I remember hearing about Somali pirates. I did not know the name of the boat, though. No.
Oh, that's the movie.
That would be interesting.
But there is a movie about that.
Okay. Yeah. No, I'm sure. I'm sure. Yeah. They possibly were meaner than the old timey pirates too. But no, I'm thinking back. Picture an old guy, in a rowboat trying to hide a chest full of gold, kind of thing.
Yeah, I know.
Okay.
Yeah, that was right.
So yeah, that kind of stuff could certainly happen along the coastlines. Again, but to jump to Goonies, then not to the extent of a whole pirate ship in there. That would be difficult. So karst features, we got caverns and caves. I don't remember the difference between a cavern and a cave right now. But two different words that mean very similar. Stalactite, stalagmite, column, flowstone. Going back to house caverns, they're mostly flowstone there. They have the little straws for stalactites, but they're mostly flowstone, look like really fancy wedding cake kind of things. Technically, a lot of these are all flowstone formations, but the more tiered stuff, they call it travertine. You might have heard of that word. That's a rock type technically, but so you see these cool flowstone formations, and then the sinkholes that we talked about. And that, my friends, is the end of the groundwater lecture. It was a long one today, 73 minutes. I appreciate your patience. We did try to keep it interesting with some anecdotes here and there.